Last time we were discussing the standards, units, and dimensions, and today we aim at describing the kinematics, the motion, and some equations. Kinematics basically describes motion while ignoring the external agents that might have caused or modified the motion. So, without going into the details of the forces and the effects of forces, we focus on motion. So, we will primarily consider one dimensional motion along a straight line. However, we will extend it further eventually. The motion in this lecture is representing the continuous change in the object's position. And we will describe the position of an object through a system of coordinates. System of coordinates will have x-axis, y-axis, and may have z-axis. So three-dimensional coordinates, well known as Cartesian coordinate system. The types of motion that are possible are translational motion. The example is a car traveling on a highway. Um, uh, it is in a straight line moving in a particular direction. Then there is a rotational motion. Example is Earth's spin about its own axis, and it is a example in which the position coordinates are changing, but the Earth is spinning. Vibrational motions are the examples of back and forth movement of pendulum, and any such movement which is about a fixed point, in which case motion is extended or non-extended, and sometimes like a spring effect, there is a compression, and then there is a elongation, and such movements are part of the vibrations. If we start the discussion, we will primarily say that we are talking about the particle model. Particle implies in physics point-like objects. The objects that are really converted to points. A large body like car, or like a huge mass, or a human being, or some stone which is with a large mass and extended mass and distributed mass, we convert this to a point and say that this point is an object which is containing all the mass, but the size is so small that it is a point particle, and it is the point which is moving. So the position. The position is basically the location. It is the location with respect to some reference point. So we choose a reference point and reference frame, and the reference frame does not change, and it's a center, or its origin remains fixed, and the object's position with respect to that origin keeps on moving or changing. So we consider the point which is the reference point to be the origin of the coordinate system, and generally the coordinate system is the x, y, and z parallel perpendicular axes, and the Cartesian coordinates. So if we are only interested in, for example, cars translational motion, then the model is that it is a point. Car is moving from point A, or position A, to position B. So it is a point-like thing which is going from one point to the other, or from F to E, or from D to C. So the particle model will be used throughout our discussion. The General trend in physics is that we plot the position as a function of time. So on x-axis, the time coordinate is shown, and on y-axis or the perpendicular axis, the magnitude of the distance or magnitude of the position is shown. This is a zero position, the coordinates original zero position. The moving up is positive direction x values, and the moving down are the negative values. And the x, for example, going from A to B, and from B to C, and from C to D, and from D to E, and from E to F. These distances traveled are different, but the time scale is same. The 10 to 20, 20 to 30, 30 to 40. So the distance between the position A and B to C changes, but the interval, the time interval remains the 10 seconds for these measurements. The first measurement is A, and then position B is measured. Then after 10 seconds, it reaches to this position, and so on. Now we can see that it's a negative direction, which means that it approached to the point 0, and then it changed its position direction from x to minus x, and it started coming back. From D to E, the car started moving back, and then to F. There are various things that we can infer from this kind of a graph. This graph is a position time graph, and smooth curve is basically a guess that from A to B, this kind of motion has been taking place. There are several representations for telling this story of position versus time. One is pictorial, the other is graphical. One is a case in which we take snaps at each time, and then we display. And the other is a graphical representation in which the graph is shown here, or the tabular form in which the distances and the time is shown, or some mathematical formula is derived. And the goal in many problems is to figure out what are the next predictable things that will happen to this kind of object. This is a data table which I have displayed here. It is a position A, B, C, D, E, F, and the time in seconds, and the distance in centimeters from the origin. So it is 30 centimeters and 52 centimeters, and then 38 centimeters, and then becoming 0, and then minus 37 and minus 53. You can see that the table represents the actual data which is collected, and it shows the position of car at various times. The time interval is 10 seconds in all cases. Position is defined as being to the right, the positive position, and position to the left is the negative position. Using another representation often is a good strategy to understand the situation of the problem. For example, we can compare different representations of motion and figure out what is going on. Before we move further on the position and other properties that are really of concern in particles motion, we have to go through briefly the vectors, because vector representation makes life easy in the study of motion. So let's go through the properties of a vector. We know very well that scalar quantity is a quantity which has only magnitude. So all quantities in physics that are having magnitudes are scalar quantities. For example, speed, say 60 miles per hour, or the distance, say 12 meters, or the age of a person, say 16 years, all are scalar quantities. If we go further, then we can define the vector, a quantity in physics that has both magnitudes and directions and a sense and its orientation. So for a vector, we need the coordinate system in which three or two or one axis is desired, and a point, a reference point, or the origin is needed. So vector examples include position, velocity, acceleration, force, momentum. Vector is going to be shown in bold letters, or an arrow above the symbol will be used to show the vector quantity. It will show that this quantity has magnitude and direction both, and some reference position through which it is being measured. For example, there are two vectors shown here. Let's first look at these. 46.5 meter towards east. A man walks towards east. On x-axis, this is east. Then another 20 meters further towards east. Then the total distance traveled is 66.5 meters towards east. So this is a vector showing 46.5 meters and the direction is east. This is another blue colored vector which is 20 meters towards east. So both vectors, when they are added, they are in the same direction, so simply we add them, we get 66.5. So addition of vectors is very easy if they are in the same direction. So here we again elaborate that the magnitude of the vector is related to the size of the arrow, how long arrow is, and the direction relative to the way the arrow is drawn towards what sense we are trying to describe. The x-axis here are shown as east. Towards the top, if we start moving towards up, the up is north, downward is south, so opposite to east is west, and that's how the directions are shown. If we are going to subtract two vectors that are in opposite direction, then simply we subtract them. For example, 46.5 meters towards east, a man walks, and then another 20 meters towards west. So if we are going to walk again from this position back, then it is going to be the opposite direction. Then we simply subtract these and we get 26.5 meters, but the net answer will be a vector directing or showing the displacement of the man towards east. So relative displacement is basically the net answer of these two vectors. We subtract them if the two vectors are pointing in opposite direction, and simply we are going to subtract their magnitude and show the direction according to the maximum vector's direction. The magnitude relates to the size of the arrow, and the direction again is the way that we draw the arrows. Here we show another rule. If the directions are not really parallel, or they are not in the same direction or the opposite direction, then if we have two vectors, for example, this is a vector, and then there is a b vector. A vector is shown in an arbitrary direction and b is also shown in. Then we look at the a plus b, and we try to copy this vector, and we try to copy the b vector, but such that the head of this vector is connected to the tail of this vector. Once we have done this, then this is going to be, if we are going to join these two, then we are going to get the resultant vector, which will be a plus b. So the way in which we are going to combine, we will reach here if we add these two vectors, so I start from here to here and then go from here to this position. So eventually this is the position. Similarly, if I have another vector shown here, a vector, and the opposite vector is in this direction, then this b vector is with the minus direction now as compared to this b. So the net is a minus b. So we can see how a and b are added or subtracted. Once we want to subtract the whatever vector we are going to subtract, it will change its direction. So the head of this a vector is connected to the tail of b, but now b is in this direction, so the position is here now as opposed to this position. So the net result will be a vector which will be joining this tail and the head. If there are two perpendicular vectors that are really having a 90-degree angle here, then we can use Pythagoras theorem, and we can reach at the results. So for example, the starting point is this, and a man travels 120 kilometers towards east, and then at this position it starts going towards north and 160 kilometers towards north. Then it finishes here. Then from start to finish, this is the resultant vector. The hypotenuse is the resultant vector, and the vector is starting from the tail of the first to the head of the second, and this is the direction. So we can find out what will be the magnitude of this vector if we know the magnitude of this vector and magnitude of this vector. And since we know the magnitude of A and magnitude of B, 120 kilometers and magnitude of B equal to 160 kilometers, then squaring and adding them and then taking an under root is basically the application of Pythagoras theorem. Pythagoras theorem says that C, the hypotenuse, C square will be equal to A square, the base, and then the perpendicular, the B square, will be added together to give us this. And taking an under root will give us the value of C, and C is calculated here as 200 kilometers. So the net result is that this is going to be a vector, the resultant vector, which will have a magnitude of 200 kilometers, although the person has traveled more than 200 kilometers, but the resultant vector has this much the direction. So what will be the direction of this kind of a vector if there are two vectors that are perpendicular to each other? So let's see. Note, when we are going to draw a right angle triangle, then we are going to convey some type of a motion that you must be drawing your components, meaning that from tail to we go head, and from head to we go from the tail of this we go to the head. So we join the head with the tail, and the resultant vector will be this from head to tail. We must have the components. So basically, if we are saying this is a resultant vector, we can also safely say that it is actually combination of these two vectors, one on x-axis and other is which is perpendicular to this. It is basically vector sum of these two vectors, as we have seen, a plus b vectors. This is a vector on x-axis, this is a vector on y-axis. So basically the vector is we can report that the vector is a basically combination of these two perpendicular vectors, one in particularly showing the direction of y and one particularly showing the direction of x-axis. The resultant is neither on x-axis or y-axis, it is in between, and its angle with the x-axis will be the direction. So with the coordinate system, some say that we must spell it out in one form or the other. In general, the two lines that are perpendicular to each other are shown to describe the coordinate system, and the north is towards the top and the south is towards the bottom. The east is towards the right direction and the west is towards the left side. So this is particular type of a coordinate system in which the directions are shown. So if I am going to draw a vector with certain angle, then we can say that this quadrant, this part is, all the vectors are pointing north of east. They are north of east, north of east. Any vector here will be north of east. Any vector from this to this position will be the east of north, east of north, east of north, east of north. Here we show the south of west, and this is the west of south. Similarly, these two, the north of west and the west of north. Similarly, here we have the south of east and we have east of south. So in general, roughly we can spell out, and you must have seen the maps where these are pointing the north of east or east of north, west of north or north of west, and so on. So basically this vector is like north of east, which is the resultant vector, and its direction is now clear. We have other ways of finding out the directions, and let us pull out those. Just pointing the north of east is not enough. How far we are from the north towards east, we need to find out some numerical value for this direction, and this we can use the trigonometric function called tangent. Tangent is basically the perpendicular magnitude of the perpendicular divided by the magnitude of this base. So opposite side and the adjacent side of the angle theta is the tangent theta, or the easy to remember is the perpendicular divided by the base. And here the perpendicular is 160 and the other is 120, and therefore we get the ratio of 1.333, and the tangent inverse of this numerical value is in terms of the degrees 53.1 degree. Therefore, the complete answer is that the magnitude of this vector is 200 kilometers and 53.1 degrees north of east. This angle is showing from the east how much we are towards the north, and 53 degrees less than 60 degrees. Okay, we move further. Another example is that a boat is moving with velocity which is 15 meters per second north in a river. So this blue colored is the north direction vector. It is 15 meters per second. Now the river is flowing and towards this another blue colored, the velocity is 8 meters per second towards west. Calculate the resultant velocity. So resultant velocity or resultant vector will be this one. And with respect to north, we have to find out. So we need this angle, not this angle, because this is 90 degrees plus this angle will make the angle from the east. We are asked from the north. So first of all, we find out the magnitude of this resultant vector. It is again using the Pythagoras theorem, 8 square plus 15 square under root, and the answer is 17 meters per second. Please verify this yourself and go through this again and satisfy yourself for this triangle. Remember that now the 90 degree is here. Tangent of theta, in this case, theta is here, so the direction which is in front of it is the perpendicular, and this is the base. Now this is the case where the perpendicular is 8 and the base is 15. So 8 divided by 15 is tangent theta, which is 0.5333, and the tangent inverse will give you. Tangent inverse is a option which is available in calculator. You can find out the theta is 28.1 degrees. So the final answer is that the 17 meters per second, the angle of 28.1 degrees west of north. It will be west of north. And that's how we solve such problems with vectors. And you can see that the resultant vector has two components. One is a perpendicular, the other is a base. Let's see another example. A storm is moving at 5,000 kilometers due east and then shifts its course at 40 degrees north of east for 1500 kilometers. And the question is, calculate the storm's resultant displacement. So this is a vector of 5,000 kilometers towards the east. On x-axis, east in the direction shown here. Now the perpendicular side, if we have the coordinate system, then this is at this position, it goes to the 1500 kilometers to this direction. So the question is, from this starting point, the ending or finishing point is the resultant vector which is going to be formed. So we need to understand that how this is going to be affecting. So first of all, we use this triangle to convert and find out this distance, and we use again the cosine and the sine. Remember that the angle here, this is the angle, and the angle is 40 degrees north of east. For this we have been given this angle. So we use this angle to find out the what will be the component on the x-axis and what will be the vertical component. So horizontal and vertical components are going to be figured out. Remember that the cosine for any such triangle, which is a right angle triangle, cosine is the base divided by the hypotenuse. And the sine is the vertical distance or the perpendicular distance divided by the hypotenuse. So we can figure out this adjacent distance and the opposite distance using the hypotenuse and multiplied with the cos theta and the sine theta. So we can use the 1500 multiplied with the cos of theta, which is cos of 40 degrees, and the opposite is 1500 sine of theta, and we can figure out how much the values are. This is east on x-axis, and this is perpendicular towards the north. Once we have done this, then we can see that the total distance on the x-axis or towards north is this much. So the total distance is this covered, and the perpendicular distance we have already figured out is this. So the new triangle is this, and we need to find out this distance. That's the storm's resultant displacement. And we need to figure out how much is this angle also. So to do this, the resultant can be calculated with the help of this value. Again, it is a right angle triangle, and so this is a 90-degree angle, and therefore a square plus b square under root will give us the hypotenuse. So resultant is equal to the a square and then b square, and the answer is 6,224.2 kilometers. Then we use the law, tangent law. Tangent law says that the perpendicular divided by the base will be the tangent. So tangent of this unknown angle theta is 964.2 divided by the 6,149.1, and the answer is 0.157. If I take the inverse to find out the theta, then tangent inverse of this thing, use calculator to find out. You will see the angle is small. It is 8.9 degrees, roughly 9 degrees, 8.92 degrees. So it is the complete answer that we have the magnitude of this storm's resultant displacement from its starting position towards 6,224.2 kilometers, and it is at the angle or the direction of 8.92 degrees north of east. So it's a small angle. Let's do one more example. It is about an aeroplane which is traveling to and has gone 209 kilometers on a straight course, making an angle of 22.5 degrees east of due north. So the distance covered is this. Now question is, how far the north and how far the east does the plane travel from its starting point? This is starting point. It has gone to this position. This distance is given 209 kilometers. The angle is 22.5 degrees that is given, and it is the angle which is with the x-axis, and the y-axis is north. So indicating that the inclined plane is there. So we use the components of a vector. A vector can be written in the components, the two perpendicular component. Let me say this is dx and this is dy. The component on x-axis towards east is dx and towards north is dy. So I use this to find out. The dx is, remember, the cos is the base divided by the hypotenuse. So d multiplied by the cos will give you the dx. Similarly, the sine is this perpendicular divided by the hypotenuse. Remember, hypotenuse is larger as compared to dy, and it is larger as compared to dx. So this will be, it can be at the most equal, but remains always less. Now if I divide dy by d, this will be dy by d, this will be the sine of the angle. And if I divide dx by d, it will be cos. So from that I can conclude that dx is basically d cos of theta and dy is equal to d sine theta, and therefore I substitute and find out the values. This is the distance position towards the east, the 80 kilometers, and 193 kilometers towards this. There are alternate representations that are really excellent in solving problems, but we have already seen the pictorial representation using vectors, and the car problem or the point particle problem can be used with these representations. So I suggest that there are tabular forms, the graphical forms, and the pictorial forms. Any of them can be employed, and the goal remains that we often try to find out the solution or the final verdict, or we can predict what will be the eventuality. Now, summing up today's discussion, we come to this important point that a vector always has is a resultant vector is basically the vector sum of these two perpendicular vectors. So x vector and y vector, when they are added together, we get r. But the r magnitude can be figured out using Pythagoras theorem. And it says that the magnitude I write whenever I write a magnitude of a vector, I write the vector as a vector bold-faced and some vector notation on top of it. And then if I draw these two lines, the mod-like lines, then these are showing the absolute value or the magnitude. So magnitude of this vector is simply r. Sometimes the whole thing is not written, so we write just r without any boldness or some vector notation. It is under root of x square plus y square, which is the magnitude of x and magnitude of y vector. Then the component x and y, as we have already seen, using the cosine and sine in this particular triangle, x is equal to r cos of theta and y is equal to r sine of theta. And this is really obvious from the trigonometry that cos is a base divided by the hypotenuse, and the sine is the perpendicular divided by the hypotenuse. So the angle then can be calculated using these the ratio of these two. If I take y divided by x, I get tangent theta and r will get cancelled, but y divided by x will give me the angle. The good representation for a vector in xy plane, this is xy plane, here I show x-axis and the y-axis, and I have omitted the north and the east notation. In this xy plane, I see on x-axis this is a magnitude of a vector x. So I can write the magnitude of vector, and if there is a unit vector, a vector which has only magnitude 1 but its direction is always along the x-axis, it is denoted and shown by the I hat, and I hat is a unit vector along x-axis, the magnitude 1, direction along x-axis. So x vector is x multiplied by this direction. Similarly, y vector is the y magnitude multiplied by the j. The j is a unit vector which is in the direction of y axis. So multiplying these scalar quantities x and y with the direction unit vectors I and j, I can have this vector plus this vector, and it is actually the resultant vector r. So one way to write a resultant vector is always like this, and you must see this again and again. I can have only one-dimensional vectors where only one magnitude and one direction is showing and completing it. These are the two vectors that are making up the vector in 2 dimensions, and one can have a 3-dimensional vector as well. In 3-dimensional position vector, we are really spelling it out like this, that x magnitude and y magnitude and z magnitudes are the values in x direction and the y direction and the z direction. Remember that the 3-dimensional position in space are really shown through this Cartesian coordinate system, in which this axis which is coming out of the paper is x-axis, and if I move from here to this it's y-axis, and if I go from y-axis to z-axis, it is again, all are perpendicular to each other 3 and the origin is at 0, and any vector is shown as sum of these 3 components, one along x-axis, other along y-axis, the other along z-axis. And that's how we sum and write a vector in 3 dimensions. We will go through this displacement in our coming next lecture, and but very briefly I must say that the displacement is then defined the change in position due to some time interval, and it is a vector quantity which has both magnitudes and the direction. So if I move from this position to another position, this is displacement. I was here at position r1, vector position, and then I move towards this r2 position, then displacement is this delta r. We will go through this again in our next lecture. Here we stop, and let's wait for the next lecture, where I will discuss further about the 2 and 3 dimensional vectors and their applications towards the physics quantities involved in physics, and will develop the kinematics. Thank you so much.